Okay, right. Well, welcome everybody. This is sort of a delayed talk because of some work commitments that I had, which was quite of apt because the JUICE mission itself got delayed, although that only got delayed by a day. So that's why we're talking about Jupiter, because of the recent JUICE launch that's gone to look for habitability in the Jovian system. So this is a talk I wheel out every now and again when Jupiter things come around. And it's about past, present, and the future exploration of Jupiter. So before I start, just think in your own mind how many times you think we've had a spacecraft that's visited Jupiter. I'm not going to do a poll or anything. I'm not going to ask right or wrong answers. Just get something in your mind. And here we are. Here's all the results. Now, only you're going to know if you're right or wrong. If that surprised you, then there's probably a few in there that you probably didn't realize, or there might be a few in there that you thought had gone to Jupiter but hadn't actually gone to Jupiter. So that looks a bit messy. So I'm going to split them up into different areas and then tackle them one by one. So we're going to talk about flybys of Jupiter, which will be first. So we're looking at the early program of the Pioneer and the Voyagers. Ulysses, which is probably one people wasn't aware of. It wasn't a big mission. It didn't even have a camera on it, so we didn't get all those pretty pictures. Cassini did a flyby when it went to Saturn, and New Horizons also did a flyby, and it actually took 3 years off its trip to Pluto when it went past Jupiter. Also look at ones that are visited in the past, so the Galileo mission, and we'll have a look at what that brought us, and also the trial and tribulations, because that mission really did have a lot of things not going for it in the early stages, but it was a real big success in the end. Current mission, which is still there, JUNO, that should have been decommissioned a few years ago, but they extended the mission. And that's now going to go out and give us some lovely pictures of the moons. Some of the closer ones, we've already got pictures of those. And also the future. So we've got the JUICE I've put down as the future because it hasn't actually arrived at Jupiter yet. So we can have a look at what it's expected to do and how it's going to do it. Then something called the Europa Clipper, which is going to be supporting the JUICE mission. And then one that's not actually gone ahead yet, but it's in the pipeline. It keeps getting put forward and rejected because of other missions, which is the EVO, it's called, the Io Volcanic Observer, and then the JCO, which is now called Tianwan-4. So we'll find out more about that a little bit later on. So why do we go to Jupiter? Well, we've had so many go to Jupiter because it's so big and it's got a good gravitational pull to slingshot the spacecraft onto its destination and just give it a little bit of a kick and speed it up, which is why we try and go there as often as we can. And also, it's also a good opportunity to calibrate the instruments while it's doing its flyby, and also it's give us some great data. So that's why we know so much about Jupiter, but also there's so much that's unanswered because it's such a harsh environment out there and the planet is such a monster. You go anywhere near it for too long, you either get swallowed up or you just get doused in radiation and all your instruments go berserk. So we'll see how they've get past those challenges over the years. So we'll start off with some of the flybys. So we had the Pioneer 10 and 11. Now they were the first missions to the outer planets, and they were sort of like the precursor to Voyagers, because the Voyager mission was sort of the grand tour. And the grand tour was they realized that there was this planetary alignment that they could make the use of and slingshot across all of the different planets to give it this extra push and visit them all at the same time as it naturally goes round. And the Pioneer missions, they didn't want to just send the Voyagers out. They sent the Pioneer 10s out just to test because nothing had ever gone past the asteroid belt. They didn't know how dense it was. They didn't know what was out there. And that's why they did the 10 and 11, 2 spacecraft, just in case one went wrong. And they did the same with the Voyager 1 and 2, which pulled off an amazing grand tour and gave us some lovely information back in the 70s and 80s on its way out from the solar system. The Ulysses mission, well, that ventured into the sun's poles, so it used Jupiter as a slingshot to take it outside the equatorial plane so that it could go around the north and south solar regions of the sun. Cassini, that spent its life at Saturn, and that used Jupiter as a slingshot to get to Saturn, to give it its little kick and to put it on course. And it also used its instruments to test Jupiter, and gives us some amazing facts back. And New Horizons, again, that used Jupiter to test its instruments on its way past, and that was built for speed. So that was it was the size of a grand piano, and as it's shot out into the solar system, straight past Jupiter, it was able to give it a real massive kick to get it onto Pluto in literally only 9 years. And I say the Jupiter flyby took 3 years off its expected time. So let's look at some of these flybys then. So the Pioneer 10 and 11, as I said, they were the precursors to the Jupiters. First time we ever wanted to send anything outside of the solar system, outside of the asteroid belt, into the outer planets, into the outer parts of the solar system. There was 2 of them. Pioneer 10 was launched in 1972, and Pioneer 11 was launched in 1973, so a little bit away apart. They both carried this plaque, which the idea was if it ever got intercepted by extraterrestrial life, then they could interpret this plaque to work out where we were. So what we have here is we have our solar system to say that our spacecraft came from the 3rd planet around this sun. This is our sun, and these are binary codes for pulsars, the top 10 pulsars that are radiating out from the sun, so that they could work out where we were. This is the spacecraft, and this is a human being at the scale of the spacecraft, so they can interpret how tall and big we actually were. And this up here is the hydrogen 21 centimeter line, so that if you watch back on the YouTube channel at my NASA Does Exploration, NASA Does Nostalgia, I go into the hydrogen 21 centimeter line when I talk about the Voyager program. So they both carried 10 instruments, while the Pioneer 11 carried an extra instrument. It had a flux gate magnetometer on it, so that it could test out all of the magnetic belts. Now, the Pioneer 10 itself, it was the first spacecraft, because it was launched before the Pioneer 11, to travel through the asteroid belt. It's the first spacecraft to take direct observations of Jupiter, and it only passed within about 80,000 miles of the cloud tops of Jupiter. So back in 1973, it sent back some images of Jupiter on an ever-increasing size that you can see over here on the picture. And during its encounter, it imaged the planet, the moons. It took measurements of the magnetosphere, the radiation belts, the magnetic field, the atmosphere, the interior. And these measurements told us that it was such an intense environment for radiation. And these findings were crucial to designing the future missions of things like Voyager and Galileo. The Pioneer 11, that began its observations in November 1974, so nearly a year after the Pioneer 10. And it made distance observations as well of the moons, the Gaia, Io, Europa, Ganymede, and Callisto. And about 5 hours prior to its closest approach, it flew past the Great Red Spot about 350,000 miles, and returned the best images that we had up until that point of all of the atmospheric features of Jupiter. It made its closest approach at about 26,000 miles in December 1974, so I say a year after it had been there. And it did a more north to south trajectory than it did the Pioneer 10. So Pioneer 10 swept across, whereas Pioneer 11 went sort of north to south. And after it had been gone behind the planet and re-emerged the other side, it returned the first images of the polar regions of the planet. And that continued its observations until about early 1975, and then it carried on onto its destination, onto Saturn. So that was the Pioneer missions. The Voyager 1 and 2, well, these were the Grand Tour missions. So it carried the illustrious gold disc So on one side, you had the sounds of the Earth. So you had people, you had birds and other sound effects from the Earth. You had lots of people saying hello in different languages. It was the brainchild of Carl Sagan, and it was Carl Sagan's son that did the hello in the English language. So it's a 12-inch disc. And if you flip it over, there's pictures on the other side, but you have to calibrate it first. And these instructions on the cover are how to calibrate it. And again, if you go to my NASA Does Nostalgia YouTube talk, or if you were present at that, I talk you through exactly how you interpret these to calibrate the disc or the record so that you can watch it. There's a record player on board so that everything is all on board this spacecraft, so that if it's ever intercepted by extraterrestrial life, they can then use it to have a look to see exactly what we were, who we are, and what Earth is like. Lots of instruments over here. So it had 11 scientific instruments, along with an RTG, a radioisotopic thermoelectric generator, which were the power supply of the earlier spacecraft, because we hadn't developed sort of solar for space missions at that point. Now, the two missions themselves, Voyager 2 actually launched 16 days earlier than Voyager 1 because it went on a more sweeping, longer journey to get to Jupiter, because then it could pass Saturn onto Uranus and then onto Neptune, whereas Voyager 1 was sent on a more direct route, because after it got to Saturn, it was then going out to Titan and being pushed up outside the equatorial plane, out into the outer solar system. So what did they do then? Well, Voyager 1, it took less than a year and a half to get there, because that was the one that went on the more direct route. As it began its Jovian imaging, it was sort of Easter time, 1978, and it was about 160 million miles from the planet when it began. And it sent back images that indicated that the atmosphere was a lot more turbulent than the pioneers had led us to believe that it was. As you can see on the pictures here, this is an image called the Blue Movie, which is what they've taken 66 images as it's rotated over a period of 10 hours. It also took another one later on in 1979, where it took 96 seconds of footage every 100 hours to generate 10 rotations of Jupiter as it went round. So it did lots of these time lapses so that you can see the features and the movement of the atmosphere. And on the 10th of February 1979, it crossed into the Jovian moon system. And in early March, it discovered a thin circular ring. It was only about 19 miles thick, but it discovered that Jupiter had a ring. And then amongst its most interesting findings was on Io, where images showed a bizarre yellow, orange, and brown world with at least 8 active volcanoes that were spewing material into space. And you can see on the picture that I've got over here, that's the plumes that was here, taken on the 8th of March 1979. And they realized it was one of the most, if not the most, geologically active planetary bodies in our solar system. And it also discovered 2 new moons, Thebe and Metis, while it was there. So that's what Voyager did for us. And then from there, went on to Saturn and continued its journey. Now, Voyager 2, on its inbound journey towards the planet, it made flybys of several Jovian moons on its way in, so that you can see these are the pictures that it took of the moons. And it made its closest approach of about 350,000 miles in July 1979. Now, on its outward leg, it encountered Io and took some lovely pictures and conducted a 10-hour volcano watch of Io, confirming what Voyager 1 had already discovered, that it was harboring active volcanoes. And you can see a lovely picture there of an eruption taken by the Voyager 2. It also revealed the Great Red Spot to be the complex storm-like feature that we know it as today. And also it imaged several smaller storms in the atmosphere, High-resolution photos of Europa revealed extensive irregular markings on its surface. So that was the Europa one up here. So I've got them, what have I got here? I've got Io, Europa, Ganymede, and Callisto. So there we go. So Europa has got all of those markings on it. And as it looked back at Jupiter on its way out, it noticed or saw, because of it was looking straight through at the sun, you can see that it's got the thin ring that's come out a lot more. So it reinforced what Voyager 1 had already shown us. It also discovered another unknown moon, and it was later named Androstea. By the time it had finished all its observations, it had taken 17,000 images of the planets and the satellite system. So you can see the difference between the Pioneer and the Voyager photos, even though they weren't actually too far apart. So once the Voyager mission had finished, Ulysses. Now, Ulysses was not primarily sent to go outside of the out towards the edge of the solar system, but it was a solar mission, and it was the first mission to survey the solar environment and to do the on the poles. So we've now got the Solar Orbiter and the Parker probe, but this one was a really early version of that, but it didn't have a camera on it. So it had lots of these instruments that could measure all of the different radio waves and the magnetometer boom out the back there and the high gain antenna to send all the details back, but no lovely color images, I'm afraid, on this one. It was launched by the space shuttle, the STS-41. It was the 36th mission of the Space Shuttle Discovery. It was the 11th mission of the Space Shuttle Discovery and the 36th Space Shuttle mission overall. And its prime objective really was to launch this Ulysses mission as part of the International Solar Polar Mission. Ooh, there we go. Now, the vehicle itself, it was designed to fly in a unique trajectory so that it could use the gravity of Jupiter to push it outside the equatorial plane and go round so that it could pass the northern part of the sun and then the southern part of the sun. And as I say, it didn't have any pictures or cameras or anything that it could take, but 13 years of orbiting, it gave us some fantastic data. Now, it was delayed for a short while because of Challenger, unfortunately, but it did eventually get set on its way in 1990. And it did pass Jupiter, but mainly it gave us solar data. So it did do a 17-day period of some Jovian work, but I haven't got anything here that I could show you. It was more of the solar stuff that I've got here, and you can see how it tracked the sunspots over that period of time, and it did a whole 17.5-year solar cycle during the course of its mission. Cassini, so another flyby mission. This one was a workhorse around Saturn. It just went on forever and ever and ever until it went for its grand finale back in the late 2018, 2019, I think it was. So it was due to spacecraft that carried also a probe that landed on Titan, the Huygens probe. And it left the Earth on 15th of October 1997. It took 7 years to get to Jupiter, but only 3 years to get to it took 7 years to get to Saturn and only took 3 years to get to Jupiter. And it made its closest approach in December 2000. And the main purpose of it was to use the gravity of Jupiter to slingshot it on towards Saturn and give it its course correction. But as it encountered its big brother, Saturn's big brother, so to speak, it used it to test its instruments, evaluate data, and also give us some extra information that we didn't know before. So it's spent 6 months exploring the Jupiter system. It did its closest approach in March 2001. It was only 6 million miles above the cloud tops. While it was there, it captured 26,000 images of its moons and the Jovian system. And you can see here the southern hemisphere. It also caught the Great Red Spot in some great detail. And although the resolution wasn't any higher than what you got on the earlier Voyager or Pioneer missions, what it did have is it had a wider color spectrum that was available to it for the instruments that were on board. So it was able to capture wavelengths of radiation that could probe at different heights into Jupiter's atmospheres and go down. And scientists were able to see lightning storms, and it helped them understand the composition of these storms, the clouds, the hazes, and lots of different things that were happening on Jupiter that they couldn't see from the data from the earlier missions. Its images revealed that there was a never be seen before dark oval next to the Great Red Spot. It wasn't as big as the Great Red Spot, but it moved about here and there. And what they thought that it was just high and low level latitude changes in the atmosphere that was associated with Jupiter's auroras. So that was Cassini. That then went on and did some great work for us over at Saturn. The New Horizons mission, well, that went on to go to Pluto. They'd been campaigning for it for ages, and eventually in January 2006, they managed to get the mission launched. And then in August, I think July or August 2006, the summer of that year, Pluto was demoted to a dwarf planet. But at least we got to go nevertheless. This was only the size of a grand piano, as I've had it described to me, and it was built for speed. There was no moving parts or anything on it. It would take pictures with its big cameras by actually just rotating the spacecraft into the direction of it, which was very challenging when you were flying past Pluto and you only had a few hours to take all of these things, all of these measurements with all of these different instruments. Again, it used an RTG, as you can see there, and this was actually the spare RTG that was used for Cassini. So the one that was left over when they made Cassini, this was the one that was used for that. It also carried this instrument here, which was a student instrument that was a dust counter, and it was called the Venetia Burney Student Dust Counter because it was in honor of Venetia Burney, who gave Pluto its name when it was discovered back in 1930. And I say it contained 7 instruments, none of them moving parts, none of them very heavy, literally just to get out to Pluto and give us some science. So it did pass Jupiter, and the spacecraft flew past to get its gravity assist maneuver in early 2007. It was traveling at 9,000 miles an hour when it passed Jupiter, and it took 3 years off the journey to get there. Now, during the flyby, it carried out very detailed set of observations over the period of 4 months while it was there, and they were designed to gather extra data on Jupiter, the ring system, the moons, and also to test the New Horizons instruments. And it also built on research of the Galileo mission, which I'll talk about later, which happened in between the Voyager mission and this one. Although observing moons from a distance, which is what it had to do because it literally was just flying past Jupiter, it did manage to catch, as you can see there, an impressive plume on Io, which was a great picture there. And it also got Ganymede, and it also took a time-lapse flyby of Europa. Now, after the encounter of the New Horizons spacecraft at Jupiter that went on out towards the Kuiper Belt and did a course correction to send it across towards Pluto. So they are all the flybys. Just a little note to where they all are now. They're all still in existence as far as I know. So the Voyager 1 is currently out here. So that got out towards Jupiter, then Saturn, out towards Titan, and then Titan flew it up to take it outside the equatorial plane. And there's a great picture, which I should include in this talk actually, of the top of the solar system being taken of Voyager 1 that looks like a nice mosaic of all of the planets lined up in their orbits around the sun. So it's 14.5 billion miles from the Earth. Voyager 2, which carried on out past Uranus and Neptune and out into the outer solar system, and that's now 12 billion miles away from the Earth. Pioneer 10 and Pioneer 11 over here, so they're 10 and 9.1 billion miles from the Earth, respectively. So you can see all the different trajectories that they've taken. New Horizons, as it went out past Pluto, it then went on to the Kuiper Belt object of Arrokoth, that looked like that snowman, if I remember rightly. And that is now, it was the fifth, it reached its 50 AU mark and was the fifth spacecraft to do that. Ulysses, that's continuing on its journey. That's going around and it circles the sun every 6 years, but the instruments are just no longer working. So we know it's there, but it's just not sending us any data back. And the Cassini, there we go. 2017, it had its grand finale where it was crashed into the planet, so that it wasn't flying around the Saturnian system to contaminate any of the moons as it was going around. So that's all of the flybys and where they all are now. Orbiters then. So we've had two specific spacecraft that have orbited there. One was the Galileo, which was the earlier mission back in the launched in the late 90s. And then we have JUNO, which is a current active mission that was due to be commissioned, but its mission was extended and it's still given us some lovely data. Now, what can I tell you about Galileo? Well, if there was ever a spacecraft that was like a cat that had 9 lives and still survived, this was the spacecraft that warrants that award. It was originally designed as a half spinning, half sable spacecraft. So the top part here would be spinning and the bottom part there would be stable so that they could take the images. So you haven't got the instruments on the spinning part, but it keeps it more stable if the top part was spinning. Well, there was issues with getting that happening, but eventually they overcame that. Then you can see that it was launched in 1989, which was a delay, and that was due to the Challenger disaster, because this again was launched by a space shuttle. So that nearly got nearly sort of put it to bed. There was also some budget cuts as well that nearly struck it off a few times. And I say it was the first planetary probe that was launched by the space shuttle in the end in 1989, and it caused a bit of controversy over the type of engine to use, because if they wanted to go there direct, they could use liquid fueled engine. If they were to go a longer route and take longer, then it would be a solid fuel engine. So they decided, for safety reasons, they would use a solid fuel because they didn't want to use a liquid engine inside a craft with liquid engine inside the space shuttle, because it would make it unsafe. So they had to choose the longer route, and that did cause a bit of debate. Another thing that caused a debate as well, as you can see on here, you can see you've got an RTG. There's another one down here. This actually had 2 RTGs, and that caused political issues about launching into space. And if it exploded while launch, what would happen to the stuff that's inside those RTGs? So yeah, nearly got pulled a few times. One thing that it did do, it was the first, gave us the first image of an asteroid, which you can see down here was Gaspra, and it also discovered an asteroid that had a moon of Ida down here. Now the Galileo spacecraft itself, it carried various instruments, And JUNO is the first, it's got JUNO down there. So JUNO was the first solar powered, but this is the first one to carry 2 RTGs. What it also carried was a lander as well that went down to the Jupiter system. So we actually got some pictures and some images of, well, so we've got some sound more than anything else, because as soon as it got so far, the pressure just crushed it. So that wasn't the end of its troubles. When it was launched, it was supposed to look like that, but unfortunately it ended up like that. Its main antenna never opened fully. So what they had to do is they had to use the low gain antenna to send a lot of its information back. It used, they didn't have digital back then. They had to record it all on the the tape recorder things here. So all the data was done on that. That got stuck. And eventually they had to decide whether they were going to rewind it and go over what they'd already done, or whether they just wait to keep the data that they've got hold of and then carry on after they'd done orbital insertion. They waited, so they lost the orbital insertion, which also meant that they lost some data from IO on the when they came in. But it turned out that everything was all right. The tape recorder worked fine, and all of the data came back on the low gain antenna. So there it is at Jupiter. And while it was there, it got a front row seat of the impact of Schumacher-Levy 9, as you can see on there, which was back in 1994. And you can see the little plumes there of the impact, which was some amazing images. So it went there at the right time. It also released months in advance. So on the approach, it had a one-time, let's release this on its trajectory course, and then off it went on its own. And the probe then gave us some interesting atmospheric data and also some sound back from Jupiter, until it actually got crushed by its immense pressure that the planet gives off. And the saved tape for the probe data. So yeah, because of the data issues with the tape, there was no actual images done on orbital insertion, which I mentioned, but they did eventually get the tape recorder fixed so that all of the data came back okay as part of the mission went on. So what did it send us then? Well, Galileo orbited Jupiter for nearly 8 years. It did a close flyby of all of the major moons. Its camera and the 9 other instruments sent back reports that allowed scientists to determine, among other things, that Jupiter's icy moon Europa probably had a subsurface ocean, which is why we're sending JUICE back there. And it's possibility that there's more water on there than there is found on the Earth. So that's what they estimate from the Galileo data. They discovered that the volcanoes on Io repeatedly and rapidly resurface. So it's really, really active, more active than any of the earlier spacecraft, like the Pioneers and the Voyagers. Although they saw it, Galileo really put it into perspective. They found that the giant moon Ganymede possessed a magnetic field, which is really important. And it's something that the JUICE mission is going to go back and try and investigate a little bit more, which is why it's got a magnetometer on it. And it's going to be doing its orbiting of Ganymede after it's gone round Jupiter. So that's Galileo. JUNO then. So JUNO, again, was another specific mission that was sent. It was launched on the 5th of August 2011. It carried lots and lots of different instruments, as well as the first solar-powered spacecraft to operate around Jupiter. And these solar panels are absolutely huge. I've got an image at the end of all of these spacecraft to scale with a human being, so you can see how big JUNO actually is. It was part of the Frontiers program, which is about sending out to, which is what JUNO was, which is what Cassini was, about exploring the outer solar system. It also carried some little minifigures as well. So the story behind these is Galileo, obviously, because of the Galilean moons. You've also got Zeus, and you've also got his wife, Juno. Now, the irony is that back in Roman mythology, Zeus was quite, or Jupiter was quite a player, and he would then hide himself around these clouds so his wife couldn't see what it is that he was doing. So the irony is then that Jupiter, we don't know what's happening there, surrounded in all of these clouds, and we've sent Juno out there to go and have a look and spy on him. So it's sort of like a recreation of Roman mythology that NASA was trying to do there. So they're a little chuckle over that. So it's gone out to Juno. So it's gone out to Jupiter. So it was the spacecraft completed its first flyby of Jupiter in 2016. So on its mission out there. Now, when it was originally sent there, it was supposed to go in a closer orbit, but one of its engines failed when it tried to do its second orbital insertion process, which means it didn't start getting as close as it was. And this is why its mission was extended, because it was only supposed to last 3 or 4 years, but it's been extended a lot further than that because it's not getting as close as they anticipated because of this second orbital insertion failure. And therefore it's not getting the radiation that they were expecting on the instruments, so they're lasting longer. As you can see there, during its mission, it looked at radiation levels for Jupiter with its magnetosphere. It's also looking at the reasons for future missions and how they could fail by measuring the amount of radiation that there is there. And there's an amazing picture here of its first flyby or its 41st closest approach. And this is JUNO, which is a really high-res camera. So it's the most high-res camera that we sent there at the moment, that will be on par with Janus that's on the Jupiter missions. And here you can see the Jupiter's atmosphere there that it took some lovely pictures of. So a lot more high-res camera that it's got. I did explain that it was extended. So this was its PJ1, so this is primary Jovian orbit 1, and it was supposed to end around here. As it went in, it got closer and closer and closer, but because it was away for so long, it was supposed to do a tighter orbit. It was able to extend its mission, and now it's out towards, it's done its Ganymede flyby, and then it's eventually going to get tighter and tighter and go into Europa and Io, and going to give us some extra data that we can then use to target specific things with the JUICE mission when it arrives there in 8 years' time. So it's extended it to 2025, and it's going to go past the inner moons of Ganymede, which it's already done, Europa and Io. Now, it's taken some pictures of all these already from afar. So it did a flyby of Ganymede in June 2021 when it came within very, very close of the planet there, or the moon there, and you can see the images that it got some lovely, lovely pictures there. And it was the closest that we'd ever been to Ganymede since the Galileo spacecraft. So all of the other flybys were well past. And finally, the spacecraft, which is scheduled to do 2 flybys of Io in 2024. And these flybys will help the up-and-coming missions of the Euroclipper and also the JUICE mission, and possibly even the proposed Io volcano observer that I touched on earlier, and I'll go into a little bit more detail later. So this is a picture of Europa's surface, and this is a pixelated pizza-like, as what they call it, the pizza moon of a long distance image that is taken of Io. So it will be getting nearer Io as it goes on its journey. So those are all the missions that have gone out there. As I promised, this is a picture of all of the spacecraft that we've spoken about. So this is the human scale, so to speak. You can see that New Horizons, say, wasn't very big. It was just built for speed to get out there. But JUNO, look at the size of those solar panels. And they needed to be that big to be able to gather all of the light while it's at that distance. So let's move on to JUICE then, very, very quickly, because we heard all about JUICE when we were watching the launch. But just a few points then. So JUICE stands for Jupiter Icy Moon Explorer. It's the first mission to go to Jupiter that ESA have been sorting out, and it's part of their Cosmic Vision program, which is about going further into the solar system. And it's the first mission that's going to go into orbit around the moon of another planet. So it's going to go around Ganymede to try and understand while it's got this magnetic field. And it's also going to look for signs of habitability in the Jovian system. So we've already said that we reckon that there's water underneath those icy structures, so that it's got things like Earth penetrating radar that can, ice penetrating radar that can get underneath that and measure how deep these oceans are and how much water there is there and the possibility of habitability. So this is the JUICE mission itself. So it's got 10 state-of-the-art instruments on board. I've got a slide on those so we can go into those in more detail. They started construction of it back in 2015. They were going to be launching it last year, but because of the pandemic and some other things, it got delayed, but only got delayed a year. And it was launched from Kourou in South America, and on an Ariane 5. And an Ariane 5 is a very, very stable vehicle. It's one of the trusted ones. But this is probably one of the last missions of the Ariane 5 before ESA upgraded to the Ariane 6. In terms of actually getting there, it's going to go through a really convoluted trajectory of a lot of flybys. And I'll say I've got something that take you through that in just a moment. But these solar panels as well, just think the JUNO ones were big. The JUICE ones have to be just as big because, again, that distance away, you don't get much sunlight. So these are its milestones. We've already passed up to the launch. So what it's going to be doing now, it's going to be doing a lunar Earth flyby in August 2024. Then it's also going to be doing a Venus flyby in 2025 and another Earth flyby in 2026. And work its way out to Jupiter to get there for 2031. It's going to spend about 3 years there, as well as going through its icy moons. And then eventually it's going to go into orbit around Ganymede around about December 2034. So that's the route it's going to be taking. Because it's going to be doing a Venus flyby, as well as going to the outer planets, they have to take that into account when they're looking at the instruments. So the instruments on board then, so they've got 10 instruments that's going to cover all of the magnetic spectrum. So you've got down here, you've got the JMAG, which is a magnetometer. So it's going to be measuring all of the magnetic fields of the entire system, and most importantly, Ganymede, to try and understand while it's there. And obviously it's on a long boom out of the back of the spacecraft, so that the instruments itself doesn't interfere with the results that gets. We've got a radio wave one, RPWI there. We've got this one over here, the particle environment package. Now that's going to be measuring plasma and its interaction with the moons, and also hopefully the plumes of Europa as well, so that if they can time it right, they'll be able to go through while some of these plumes, and they'll be able to measure some of the plasma that comes through there. You've got Janus, which I've mentioned, which is a really high-res camera, and you've also got the UV and also visible light. So it's all covered there. As well as you're going to be having RIME, which is the radio penetrating radar that I was talking about, and that's going to be able to look through the icy shell of the moons up to about 9 kilometers subsurface. So that's really impressive. It's also carrying this RADEM, so it's not an instrument as such for the planets, but it's going to be measuring the amount of radiation and monitoring it while the spacecraft is going through the Jovian system, so that if anything looks like it's higher than it normally should be, it can automatically shut down the instruments to protect them and help them. So one thing that they've learned, because the environment out there is really, really harsh. And it's going to be carrying this PRIDE, which is an experiment to test interferometry that's going to help us accurately measure spacecraft while they're out there in more detail. So it's like it's a solar system sat-nav, so to speak. So that's what it's going to be doing. So yeah, lots and lots of stuff going on the JUICE mission. In terms of protection, so you've got shields to protect the instruments, so make sure, because of the high radiation. You've got the long distance, because it's so far away. Look at these solar panels, 2.5 meter antenna that's going to be sending things back, as well as the solar panels that are 85 square meters in area to collect as much light as possible. And I told you about the harsh temperatures, so it's got a multi-layer insulation thermal blanket that's around it, not only for the minus 230 degrees of Jupiter, but they also have to think they're going past Venus, so they have to allow for the plus 250 degrees centigrade of the Venus flyby. So they have to take these into account when they design what's actually going to be going on board. So what's JUICE going to be doing while it's out there? Well, it's hopefully going to be answering these 5 questions, or at least trying to. Why is Ganymede so unique? We've already mentioned that it's got its magnetic field. What are the ocean worlds like? So we already know that the ocean worlds exist. We've had the data back from the previous spacecraft, but this one is specifically designed to look through and get the data from that. Has Jupiter's complex environment shaped its moons? Because it's a harsh atmosphere out there. It's such a big planet. It's building moons all the time. Every time I see a figure, it's just got more and more and more. I think it was up to 72 or nearly 80 when I last looked. It's probably up to 90 now, because it just captures things whenever it goes near, which is why it's so good for us, because it's protection from any objects that come out from the outer solar system. Jupiter just sucks them in and before they get to the Earth. And also you've got the its own magnetic field, which stretches out, I understand, past Saturn. So yeah, all of that complex environment going on. I'd say, is it a typical gas giant? It's the largest gas giant. And whenever we talk about exoplanets, we talk about hot Jupiters and things like that. So if we can understand our own Jupiter, maybe it'll help us to understand what it is that's going on outside our solar system. And also, which is the big question, could there or has there ever been life in the Jupiter system? So it's looking for habitability. So there we go, the JUICE mission in a nutshell. It's an ESA-led mission that was launched from French Guiana on an Ariane 5. It's got 10 instruments on it to visit the icy moons of Jupiter as part of the ESA's cosmic vision between 2015 to 2025, which is what the cosmic vision time frame is. It's going to do the first lunar Earth gravity assist, so it's going to be really using an unusual trajectory to get out there, which is why it's taking so long, not the sort of 1.5, 3 years that it's going to we can take on the direct route. It's going to be changing its orbit from a planet to a moon when it goes around from Jupiter to Ganymede, and also when it orbits Ganymede, it's going to be orbiting the first moon other than our own. As this is an OU course, might as well tell you about a course that I did. It's a free course on the Open Learn. It's Moons of Our Solar System, which covers all of the moons in our solar system, our own, and goes very in depth into the Jovian moons. You get a free certificate of participation, and it's also a badged course as well. So future mission then. JUICE, which we know, it's on its way out there. It's getting there, and they reckon it's going to be there by 2031. Euroclipper, that's a NASA mission that's going out there, and that's going to be complementing the JUICE mission. They do this quite a lot. They've done it with the Solar Orbiter and the Parker Solar Probe, and that way you can see the same things from different angles and get sort of like a 3D image of the area. But this one's specifically looking at Europa, whereas JUICE is looking at all of the icy moons, but concentrating mainly on Ganymede. This is the one that I was talking about, where it's still a proposed mission. It just keeps getting put off and put off and put off. Last time it was proposed, it was part of the discovery package of 15 and 16 selection process, which it lost out to Da Vinci and Veritas that are going to Venus. And then finally, this one over here, the JCO, which is the Jupiter Callisto orbiter. And that's going to be a China mission that's now been named as Tianwen-4, and they are proposing to launch that in 2029 to reach the Jovian system in 2036. So that's it from me. A complete overview of what we've done Jupiter so far. And I'm just going to leave you with a quote from Galileo, which is a plaque that's actually aboard the JUNO spacecraft, which is part of his observations that he made of Jupiter from his book. And it's, on the 11th, it was in this formation, and the star closest to Jupiter was half the size than the other and very close to the other, so that during the previous nights, all of the 3 observed stars looked of the same dimension and among them equally afar, so that it is evident that around Jupiter there are 3 moving stars invisible till this time to everyone.